So with an equation, and I'm restating this because I'm now recording a little bit of it, with initial velocity of 90 feet per second, and then initial height of 50 feet. So that was your given height function with respect to time. When the question asks, when does it hit the ground, you're thinking, when is the height a whomping 0. So negative 16t squared plus 90t plus 50. The quick and easy way is to go ahead and just do the quadratic formula. If you've not done that in a while, or hey, how about I do this as a quick review. Sometimes people like to do completing the square. If you've never done that before, it's actually faster, and it is the exact same thing as the quadratic formula. So completing the square is I would move the 50 over here, and then I'd have negative 16t squared plus 90t. If I divide everything by negative 16, I would then have t squared plus, actually it'd be minus then, because it's positive, minus 90 over 16 t will equal 150 over 16. I'm just going to leave that as is. I mean, if you don't like it because it's two even numbers, you could reduce that. But completing the square is if you take half of that middle term now that my coefficient is 1, half of the middle term is 45/16, and square it to both sides. That's a 16. I do that because then this now, and I did it again, this should be negative because I'm dividing by a negative. I keep writing it as a positive. That's a negative. It should now be factorable like this. T plus 45/16 and t minus 45/16. No, I'm taking that back. It is plus. Sorry. I'm like, maybe I shouldn't have gone. It should be. Let me get rid of this. Since it's minus, that means both of these are minus. So that's a minus. 45/16. It's called completing the square because then it's something squared. So that'll equal whatever that large fraction is on the left-hand side. To then solve for t, I would take the square root of it. So I'd have the square root of 45 over 16 squared. Again, this is just going to be a fraction or a number, plus 150 over 16. And it's plus or minus.
Where'd you get the 150?
That's just 250.
It's just 50?
Yeah.
It's just 50 because, yep. And then that's going to equal t minus 45/16, and then you'd add 45/16 to both sides. So you'd have that, whatever, and this is actually where the quadratic formula comes from. If I did this with just a, b's, and c's, you could derive the quadratic formula out of it. Now, if what I just did is you're a little too much to handle right now, then ignore it. Some of you may have seen this before and go, oh yeah, I remember doing that. And you have like this internal moment of pride. That's great for you. But if not, don't worry. Just go back and do negative b plus or minus the square root of b squared minus 4ac all over 2a. So either this or the quadratic formula, and you're going to get a value of t, and you're going to get two values of t. One will be positive and the other one will be negative. Obviously, the positive number is where it's going to land and hit the ground. The negative number would be if I think about my building or think about my function. Let's think about my function. This is h of t. This is time t on my x-axis. And that function starts at 50, goes up and comes down. If I were to imaginarily draw that parabola back, that's the t, that's the negative t value. That's the other root of this equation that out of context you would give as an answer, but within context it can't be an answer. We cannot go back in time, but we're also starting at the top of a building. But that's the other extraneous, or that would be the extraneous solution in this case. Maximum height will occur, and this would be taking into consideration the two t values. So for that, did someone actually get the two t values at this point? So those are the two confirmed values for the time. If we're asked to find the maximum height will happen like we had up in the question, halfway between those 2 points. Because that's the center of my parabola. So if I find the average of those two numbers, 6.13 plus, or yeah, negative 0.509, and then divide by 2, the halfway point between the two roots is 2.81. So at time 2.81, it will be at maximum height. All right. And that's, again, remembering that it's a parabola is symmetric around the line of symmetry. And the line of symmetry goes through the vertex. So that means that's the halfway point between the two roots. Take this number, place it into your equation, and that'll give you the maximum height. In terms of simplifying logarithms, so this one was from the review sheet that we had. Remembering, so some of the properties of logarithms, if I have log base b of a to the n, that can be rewritten as n times log base b of a. That would be powers raised to powers. As exponents, that's what we have going on here. We have other logarithmic principles, log base b of two things multiplied, a times n, where n is a number, a is a number. That can be rewritten as the log base b of a plus the log base b of n. And that's related when we do exponents of, when you have same bases and multiply, you add exponents. Remember back when we had like 3 to the 7th times 3 squared, that's 3 to the 9th. That's the same idea. When you have same bases and we're multiplying, we add exponents. And because logarithms and exponents are basically inverse operations, when we add logarithms, we're really multiplying. It's the same principle that goes into place there. And then the same thing goes as subtraction. Subtraction of logarithms is division. And up here, I have subtraction. There's a lot of ways I could tackle this problem first. If I do that first, I can go natural log of 6x to the 9th divided by natural log of 3x squared. Because the property of subtraction is division in logarithms. And then in the numerator, I have multiplication. So I can rewrite that as natural log of 6 times natural log of x to the 9th. In the denominator, I can rewrite that as natural log of 3 times natural log of x squared. Using, again, there's a couple ways you could go. I see this right away. I'm like, all right, again, I'm only multiplying and dividing. So I can actually bring this back together and do this then as subtraction. So this chunk right here is then natural log of 6 minus 3, which is the natural log of 3, which is just going to give me a number. All right. The other part here, I'm going to take this only, and I'm going to write that as natural, so that if I'm staying with what I had before, 9 natural log of x. Because x to the 9th is this. The whole thing is being taken to the 9th power, so I can just take that exponent out in front. I can't do the 9 out in front at the beginning because everything is not to the 9th power, only the x's. And then this becomes 2 natural log of x. And then I can reduce. Natural log of x divided by natural log of x is 1. 9 divided by 2 is, 9 divided by 2. But now I'm at a point where if I actually had a calculator, I could do that and get some just plain old numeric answer. All right, the question's related to talking about zeros, intercepts, asymptotes, end run behavior, those kind of things. So here is an equation that we just kind of formulated up. Zeros are when it crosses the x-axis. So a 0 happens when my numerator is 0. So then I look at the numerator and say, what makes this 0? This 0 is when x is 4. So at x equals 4, 1, 2, 3, 4, I have a 0 because it crosses the x-axis at 4. And then I look at the other one and say, what makes this 0? That would be negative 3/2, which is negative 1.5 right there. So I have my graph crossing the x-axis in two different places. A horizontal asymptote will occur at a place where the numerator does not exist. Is there any restriction on any value I can put in for x? And the answer is no, there's not. So I'm not going to have a horizontal asymptote. A horizontal asymptote would occur oftentimes if I have, like in the numerator, if I got a square root, then you look at that and say, oh, well, you can never take the square root of a negative number in a real number system. So at some place, you're going to get to a place and say, oh, well, it can't be that because I'm here. Or possibly you have a logarithm. All right, logarithms have limits for what they can do, and that might be a determination for having a horizontal asymptote in the numerator. So horizontal asymptotes are related to the numerator, just like zeros are related to the numerator. Vertical asymptotes are related to the denominator, because here we're saying, what can x not be? Again, we're looking at 0. What makes my denominator 0? At x equals 1, I have a vertical asymptote because, I meant to have my pointer on that one. Put in 1, 1 minus 1 is 0. I'll have something divided by 0, and we know that we explode or implode or something terrible happens when you divide by 0. We cannot do that. We also look and say, at x equals negative 5, so I'm at negative 1, 2, 3, 4, 5. At x equals negative 5, I will also have a vertical asymptote for what's going on there. And then, if I had to sketch this graph, I would be looking at what is happening when the graph is near 4. All right, when it's near 4, it's going to be somewhat parabolic. All right, so it's going to have some kind of a curve going on, but you're going to be wondering, is it going up or is it coming down? Or is it going down and then coming back up? And the answer is revealed in my end behavior. So my end behavior here is the fact that if I look, and if I were to multiply this whole thing out, which I'm not going to do, my leading coefficient in my numerator is not going to, I don't want the pen tool, is 2x cubed. Because I know that this will be x squared, then it'll be times an x, and then the leading coefficient, so my leading term is 2x cubed. In the denominator, I'm going to have an x that gets squared. I'm going to have another x, so I'm going to have x cubed, and the whole thing gets multiplied by 2. It's also 2x cubed. The limit as x approaches infinity, this number cubed, so, take 1,000,000 and you cube it, 1,000,000 and you cube it, you multiply it by 2, that's the same number. All of the other terms will still exist, but they're going to be much, 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 much smaller. So yeah, we're going to be adding and subtracting, so they're not going to be identical, but as we approach infinity, they become so inconsequential that this defines my end behavior. Somewhere way out here, as x approaches infinity, f of x will approach 1, because any number divided by itself is 1. Now, it's a long ways out there, But somewhere out here, I'm going to have the idea of a horizontal asymptote at 1. And then I got to figure out, is it going to be coming at it from the top or the bottom? It's likely going to be coming at it from the top, and I can verify that a couple different ways. If I'm at, let's see, 1, 2. If I'm at 2 for x, this is negative, but squared is positive. This is positive, so I'm going to have a positive in the numerator. If this is 2, 2 minus 1 is positive, positive. So it's going to be positive over positive. So at 2, I'm up here, somewhere positive. Well, that makes me concerned because I'm not going to come down here and then come back up. Otherwise, I'd have another crossing out here. What that means is what's going on at x equals 4, it's parabolic like this. Going to come down and kiss and then go back up. I was supposed to hit it at that intersection point. And this will go up that way towards that intersection point. Somewhere out to the right, it's going to come up and then come back down and approach. That's my guess. Without plugging in a bunch of numbers, it's possible that it comes down and then flattens out right away. But I doubt it. That would not give us enough of a parabola there for this to happen. At either point, this has got a parabolic view at that point because it's squared. The same thing will happen here at 1. At x equals 1. Oh yeah, never mind. That's my, yes, sorry. Talking myself around backwards. If I had to figure out what's going on in between here, so at this point I'm at 2/3 x, which is linear, so it's going to be crossing about like this. So the function's going to be coming down, crossing, going up. And I keep grabbing the wrong tool. Pen. And then out there to negative infinity, it never crosses the x-axis. So I'm either going to be always negative or always positive. And because the leading coefficients are both x cubeds, and I'm putting in increasingly larger and larger negative over negative. So a large negative over a large negative is a positive 1. So it'll be something up here that goes out and approaches 1. All right. And if I were asking you to do this without actually using a graphing tool, I am fully allowing you to have some liberty in discussing what you think might be going on, more looking at can you focus on how you know these are zeros. Oh, and then I need my y-intercept. Put in 0 for x. So when I put in 0 for x, I get 1 squared, which is 1, times 2 is 2, times 5 is 10. My denominator is 10. When I put in 0 in the numerator, 0 minus 4 is negative 4. Squared is 16. 16 times 0 plus 3, 16 times 3, that's 48. So I'll have 48 over 10, or about 4.8. So I've got my x-intercepts, my y-intercepts, my vertical asymptotes. There aren't any horizontal asymptotes, although my end behavior here approaches 1, and my end behavior way, way, way out there to the negative also approaches 1. So f of x, the way that would be written, the limit as x approaches infinity of f of x is 1. That's really messy. The limit as x approaches negative infinity of f of x is equal to positive 1. The limit as x approaches positive infinity of f of x is also 1. Because I have the exact same thing for my leading coefficient, numerator and denominator. And a negative divided by a negative is a positive. Positive by a positive, also positive. Now, granted, we're talking about positive infinity over positive infinity, so we're talking really theoretical when you get out that far, but that's what we're approaching. So for doing exponential growth or exponential decay, there was the example from the review sheet that we had where it was a radioactive decay. The problem, I think it's the first problem. I'm actually looking at the review. It says the scientist begins with 110 milligrams. So that's my initial amount. So if I'm thinking about exponential decay of a radioactive substance, so my substance over time will be 110 milligrams times B, which is ever my rate, times time. Which means we could figure this out. If I put in 0 for time, 0, B to the 0 is 1, my amount will equal whatever I had at the beginning. So that's how I know that the 110 is my A. Or I just plug it in because I know that that's my initial amount. And then I'm given the information that after 31 hours, so at T equals 31, I have 55 milligrams remaining. So S of T would be 55. Plug this in, 55 equals 110 times B to the 31st power. Divide by 110, that's a half, equals B to the 31st. And then to find B, I'm going to take the 31st root of B. And if I take the 31st root of 0.5 raised to the parenthesis 1 divided by 31 in parenthesis, B equals, hold on, 0.97789. I always get asked, how far should we round? When in doubt, don't. We're not in a science class where sig figs really matter. They do matter, but for what we're trying to do, they don't matter right now. So that's my B. So my actual then original equation will be substance is equal to 110 times 0.97789 to the T power, where T is number of years. Second half of the question says, how many milligrams will remain after 42 hours? So I want to find S of 42. Plug 42 into that, and you can crank that out on a calculator pretty quick. Where it gets more challenging, like the next step of this equation, would be when it asks, when will it be, so T equals unknown, when are there 5 milligrams remaining? So now I'll have 5 milligrams equals 110 times 0.97789 to the T. Solve for T, divide by 110. 5 divided by 110 is 0.045, and the 45 repeats, but not the O, equals 97789 to the T. When I have variables and exponents, now is when I do logarithms. If I take the log of both sides, log of 0.04545 repeating equals log of this number again, 0.97789 to the T. This is where I recall my properties of exponents. This T travels out in front, so it becomes T times, and when I do that, it's no longer in the exponent. Now I've got T all by itself. Divide both sides by this mess. And then you can either do both of those separately, or because I'm dividing, you could do log of 0.045045 minus the other one, or just plug it in your calculator. It doesn't matter really at that point, and we'll find that the final answer for T equals point anything?
0.2513.
There we go. We'll go 0.25 because a quarter of a year, that's a substantial amount of time. If I don't ever specify decimals, don't round to the whole number. give me at least a couple. But as always is the case, I'm typically looking for process and procedure more than final answer anyways, but rounding oftentimes is your downfall. So our final answer is at 138.25 years. I am all the way down to a 5 milligram amount of whatever this substance is, radioactive substance that has a decay. So for investing, if I have a principal amount that I invest at a certain rate and it's compounded at a certain amount of time. So if I were to compound quarterly, my equation would be my principal amount times 1 plus r over 4 times 4t, or to the 4t power, because it's n times t. If I am going to work, and that would be my amount. If I do it monthly, that denominator changes to 12, and this becomes 12. If I do what's called continuous, if my interest is compounded continuously, so interest compounded continuously, that would be A equals P times E to the RT. That's the equation for compounding continuously, where they're just always going at it. Aside from knowing this, I mean, from a practical side of things, not many places compound interest continuously. But it's an interesting proof for how you can go from here. So as R over N, as N approaches infinity, to the NT actually approaches E to the RT. I say fun derivation because I think it's fun. But gets back to when people say, well, when does E ever really show up? It just seems like another random thing like pi. I mean, pi is very powerful in terms of being the ratio of diameter to, or circumference to diameter. E shows up more ways because then when we did Euler's method for, I can't remember what chapter we were in on that, there's where E kind of shows up again for one of our conversion factors for moving from polar to complex. To convert an equation from Cartesian to polar coordinates, in Cartesian, we oftentimes had y equals. When I get to polar, I'm going to want to have r equals. So then I go, all right, what are my conversions from polar to Cartesian? X equals r cosine theta. Y equals r sine theta. Plug those in. R sine theta equals 3r cosine theta plus 2. I'm going to move my r's all to one side. R sine theta minus 3r cosine theta equals 2. Factor my r out. Sine theta minus 3 cosine theta equals 2. So r equals 2 over sine theta minus 3 cosine theta. And if I'd go to Desmos and type that in, it would give me a straight line because y equals 3x plus 2 is a straight line. So that's converting from Cartesian into polar. To go from polar into Cartesian, let's go a new slide. Polar to Cartesian, hold on. If we have something like this, r equals sine of 2 theta. If I need to go from polar to Cartesian, x equals r cosine theta, y equals r sine theta. So I can choose, if I'm just going to rewrite these. I'm going to take this one down here. X over r equals cosine theta. Take this one down over here. Y over r equals sine theta. The one that helps me out here is this one. And the reason why is because my equation has sine in it. Now, this is sine 2 theta, so instead of sine theta, it will be sine 2 theta. But I will have, hold on, let me pause for a second. There you go. So cosine of 2 theta is 2 sine theta cosine theta. This will equal r. I can then plug in the sine theta and cosine theta. So this would be 2 times, and my sine theta is y over r, and my cosine theta is x over r, and then this equals r. I can have then r cubed equals 2xy. R cubed is r squared times r. And the reason why I write it like that is r squared is sine squared plus cosine squared, which is 1. And so when I'm doing it, I'm thinking about x squared plus y squared. As my equation equals 1, that's the same as sine squared theta plus cosine squared theta equals 1. Now, granted, I got them switched back and forth because we typically write sine first and cosine next, but it's the x and the y. So my r squared will be x squared plus y squared. I have that times r equals 2xy. I still haven't gotten rid of my other r, though, so I got to find a way to do that as I'm working my way through. I'm going to pause for a moment. All right. And then I am going to actually pause on that one. I'm going to set it up another way over here. There's other ways to go. I could rewrite this as r of r equals, oh gosh, my parentheses are terrible. Just call it sine of alpha, and we'll say alpha is 2 theta up here. For that to be the case, if we used this value here for sine and moved it up and replaced sine theta and called this instead y over r equals r, I'd have then r squared equals y, and it would be x squared plus y squared equals y. Knowing that when this gets converted back in, so this is this will be the super short way to get it as a single value, but you'd have to recognize that when you're doing your conversions, if you're putting it back into polar, that whatever you do when you're doing your function, it's not just the alpha, it's actually going to be twice that value when you're doing it. If you got to here and got stuck, you're really not that far from this. It might feel like you are, but you're not. We would end up getting to the same answer as well. And this is more my nature. I tend to go at things and try to derive it from the full on, including all aspects of it. This is the shorter way, but recognizing you can just do a substitution here. So now it's just a sine alpha instead of a sine 2 theta, so I don't have to do the double angle formula to get back to here.